So in the last two classes, we have discussed about the theory of moving coil galvanometer and the damping correction that should be applied to the uh, moving coil ballistic galvanometer. Okay, now we will discuss about the current and voltage sensitivities of a moving coil galvanometer. The figure of merit or current sensitivity, which is represented by S suffix C, of a moving coil galvanometer is the current that is required to produce a deflection of 1 millimeter on the scale, which is kept at a distance of 1 meter from the mirror. So you should remember the arrangement of the mirror and scale in the moving coil galvanometer, which we have already discussed in the last class. That is, the mirror which is attached to the coil is kept at a distance of 1 meter from the scale on which the deflection of this mirror will be produced. So the current sensitivity is the current required to produce a 1 millimeter deflection on the scale. So it is expressed in unit of microampere per millimeter. Similarly, the voltage sensitivity can be defined as the potential difference or the voltage that should be applied to the galvanometer to produce a deflection of 1 millimeter on the scale. So voltage sensitivity is the voltage and current sensitivity is the current which is required to produce a 1 millimeter deflection on the galvanometer scale. So the experimental setup to find out the current and voltage sensitivity is shown here. Here this is an accumulator or cell and it is connected through a key to two resistance boxes P and Q. These are two resistance boxes and R is another resistance box which is connected here to the moving coil galvanometer through a commutator key. So this is the arrangement and how this experiment should be done. So in the experiment what we are doing is a low resistance, say of the order of 1 ohm is introduced in P and a high resistance, say nearly 1000, that is 9999, so that the combination of P and Q will give you a value of 10,000 with no resistance in R. So what we are doing is, in this experimental setup, the combination of this is set up as a low resistance in P and a high resistance in Q, so that the combination is 10,000 and no resistance in R, and the cell is connected. So a deflection will be produced in this galvanometer which will be noted as theta. Okay, now the voltage sensitivity can be calculated using the formula E into P by P plus Q into theta, where theta is the deflection produced by as just explained before. Because this formula comes because V is equal to I into R. The voltage is I into R. Here the current is E by P plus Q, because E is the potential we are applying and the resistance here is the series combination of P and Q. So the current is E by P plus Q according to the formula V by I. So the current is this value and again R. Here R is P. Okay, because the you can see that the moving coil galvanometer is connected across P through the commutator key. So the voltage developed will be I current developed will be I into P plus Q. Okay, and the voltage will be I into P plus Q E by P plus Q into P. So I into R will give you the formula E into P by P plus Q and per deflection. So theta will be there in the denominator. So it is expressed in 10 into 10 to the power 6 unit. So the value of the voltage sensitiveness will give you by this expression, E into P by P plus Q into theta into 10 to the power 6 microvolt per millimeter. Now the resistance in R is adjusted such that the deflection becomes theta by 2. Now the resistance R is the resistance connected to the galvanometer here through the commutator key. So now what we are doing is the resistance in R is adjusted such that the deflection produced in the galvanometer is half of that of the previous deflection, that is theta by 2. First deflection was theta and now it is theta by 2 such that the resistance is adjusted. The resistance in R is equal to the galvanometer resistance Rg, because here some voltage will drop across the resistance R and the remaining charge or current is flowing through this galvanometer which will produce the deflection theta by 2. So this resistance across which the potential is dropped is equivalent to the resistance of this galvanometer because they are connected in parallel. So the resistance of this resistance box is equal to the resistance of this galvanometer. That's why some potential is dropping here and half deflection is produced here. So we can write R as Rg. So the current sensitivity, so this is the voltage sensitivity. This is the expression for voltage sensitivity. Voltage into V by R will give you the current. So this divided by the resistance will give you the current resistivity. So here the resistance is Rg. So this is the expression for measuring the current sensitivity of the BG. So the experiment can be repeated for various values of P and Q, keeping P plus Q a constant value. So this is the experiment setup and how we measure the current and voltage sensitivity of a BG. Okay, now we will discuss the measurement of charge sensitiveness, or it is known as figure of merit of BG. Measurement of charge sensitiveness of BG. The charge passing through a BG is given by Q is equal to T by 2 pi C by NBA into theta 1 into 1 plus lambda by. We know this equation, we have already discussed. It is in the theory of BG. So these terms together can be noted as K, which is the charge sensitiveness or figure of merit of the galvanometer, which is a constant. It is also known as the ballistic reduction factor of the galvanometer. So this value K is also known as ballistic reduction factor. The charge that should circulate through the coil to produce an undamped throw of 1 millimeter in the spot of light on a scale placed at a distance of 1 meter from the mirror is called charge sensitiveness K of the ballistic galvanometer. This is simply we can state this simply as the charge that should be flowing through the coil to produce an undamped throw of 1 millimeter on the scale, which is kept at a distance of 1 meter from the mirror. That's the charge sensitiveness. The definition is similar to that of voltage sensitiveness and current sensitiveness. Okay. Now the connection diagram or experimental setup for measuring the charge sensitiveness is shown here. Here similar to the previous figure, here this is a cell, this is the key, and P and Q are two resistance boxes. resistance box, and here is a capacitor, and here is a charge discharge key uh, connected through a vibrator V, which is marked as V. Here it is explained the terminal charge of the capacitor is connected through a PD, potential difference across P. Okay, here a capacitor of non-capacitance is connected to P through the vibrator V and a charging terminal CH. This is the charging terminal, this is the discharging terminal, and this is the vibrator. Okay, now the charge on the capacitor can be discharged through BG included in the circuit through the vibrator and discharge terminal of the charge discharge key. So when the cell is on, the charge on the capacitor will get charged, and the charge on the capacitor can be discharged through BG through the vibrator and discharge terminal of the discharge key. So this charge accumulated on so this is the capacitor which is connected to the BG through the discharge key and the vibrator. So this charge accumulated on the capacitor can be discharged through BG through this discharge key and vibrator. Okay. Now the commutator series also included in the circuit in order to reverse the direction of the charge or current flowing. Okay, so this commutator key is for the purpose of reversing the direction of the charge. Now how we'll do the experiment? To measure the charge sensitiveness, a combination of 1000 ohm in P and 9000 ohm in Q are included, so that the total resistance P plus Q is 10,000, just as in the previous measurement. So the capacitor is charged and immediately discharged through the BG. The first throw theta 1 is noted. So the capacitor is allowed to charge and it is allowed to discharge through the discharge key, so that it will the charge accumulated on the capacitor will flow through the BG through this discharge key. And this experiment is repeated with another combination of P and Q, such that the combination is 10,000, that is P as 2,000, 3,000, etc., keeping P plus Q constant. Okay, now the mean value of P by theta 1 is calculated. So let the capacitance of the capacitor be C microfarad. Let the capacitance value is C microfarad. Now the charge on the capacitor can be calculated using this formula. This formula comes from we know V is equal to I into R, so that the I is V by R. I is V by R here. So V is E and R is the combination of P plus Q. So P plus Q will give you the resistance. So I is E by P plus Q. So V is I into R, so that E into P by P plus Q. And the charge on the capacitor Q is equal to C into V. So multiplying this with C will give you the charge on the capacitor. Okay, this charge produce a throw theta 1. This charge will produce a throw theta 1. So the undamped throw theta can be represented in terms of theta 1 as theta 1 into 1 plus lambda by 2. The charge required to unit deflection K can therefore be the charge sensitiveness is K, which is the charge required to produce unit deflection. So that we can write K into theta 1 into 1 plus lambda by 2 is equal to EP by P plus Q into C. Okay, so we will get K as EC by P plus Q into P by theta 1 to 1 plus lambda by 2 microcoulomb per division, which is the charge sensitiveness or figure of merit of the ballistic galvanometer. Okay, the value of lambda is obtained by observing the first throw theta. This is not theta 1, this is theta, this is comma. And then the 11th throw theta 11, and using the relation lambda is equal to 1 by 10 log to the base E theta by theta 1, which we have already discussed in the topic damping correction. Okay, so the decrement lambda can be calculated using this. So this is how we are calculating the charge sensitiveness of a BG. Okay. Now we will discuss the measurement of K using Hibbard's magnetic standard. Hibbard's magnetic standard or HMS method. Hibbard magnetic standard method. So what is Hibbard's magnetic standard? So it consists of a block of hard steel with a cylindrical slot cut in. So this is the hard cylindrical core, hard steel block with two cylindrical slot cut into it. So this is a complete block and two cylindrical slot cut into it, and the block is magnetized so that the field is radial as in figure. So this block is magnetized such that the magnetic field is radial. So here I have shown the polarity of this magnetic field. Here south. In this region, here it is, this is south, this is north, and for this region this is north and south. Okay, the arrangement is done such that the magnetic field is radial. A brass tube has a single layer of coil of N turns wound upon it, with its ends connected to the terminals T1 and 2. So these are two terminals T1 and 2, and a coil of N turns. This is the brass tube. This is the brass tube, and a coil of N turns is wounded on this brass tube, and then the end of this is connected to the terminals T1 and 2. T1 and T2. So the brass tube, which can freely slide into the slot, is always dropped into the slot from a certain fixed height. So what we are doing is, the brass tube is free to move, so which is dropped from a height into this slot. So here there is a magnetic field which is radial in direction, and this is a brass tube in which we have n number of coils wound on it. Wounded on it. So we can drop this cylinder or the cylindrical brass tube inside this slot. So what we are doing is we are dropping this brass tube from a height to this slot. So what will happen? The magnetic flux will is disturbed, or there is a change in the magnetic flux inside this slot. So the magnetic flux between the north and south poles of the magnet is determined using a solenoid inductor. The two terminals T1 and T2 are connected to a BG through a resistance box R and a commutator as in figure. So this is the this is the setup of HMS, Hibbard's magnetic standard. So we have explained this. This is a hard steel core with a two cylindrical slot and radial magnetic field inside it, and a brass tube which is having coils wounded on it. So when we drop this tube inside this slot, the change can be occurred to this magnetic flux in this region. So this is HMS, and this HMS is connected to a BG through a resistance box uh, R and a commutator as in figure. So this is the figure. This is HMS. And this is terminal T1 and T2. This is connected to a BG through a resistance box R and a key. Okay. So the brass tube is now dropped into the slot between the north and south pole. So this is the slot. I have drawn it as a cut here. This is a cylindrical slot. So this brass tube is dropped into this slot. The change in magnetic flux linked with the coil is phi n. So that the change in flux linked with the coil can be represented as phi n, where phi is the magnetic flux in the Hibbert standard. Okay, so if G is the resistance of the BG and the coil induced a charge in the coil can be calculated using the formula phi n by R1 plus G. This formula comes from the Faraday's law of induction. According to Faraday's law of induction, whenever a magnetic flux linked with a coil or a field changes, there is a production of EMF there, and this EMF is proportional to the change of magnetic flux linked with the coil. That is, EMF produced will be proportional to d phi by dt, where phi is the magnetic flux linked with that coil. Okay, so the EMF is equal to I into R, and I is equal to dq by dt into R, where dq by dt is the current, that is the charge per unit flow. Okay, so from this equation we can write dq by dt is equal to d phi by dt into 1 by R. Okay, so the charge induced, this is phi and this is q, so the charge induced is d phi by R. Okay, so that's how this expression comes. So the charge induced will be in the coil will be the change in flux, which is represented by phi n, and the resistance. Here the resistance is the resistance in the circuit, introduced in the circuit, plus the galvanometer resistance, the series combination of these two resistance. So that's how this expression comes. So this is the induced charge in the coil. Let theta 1 be the corrected first throw. Let theta be the corrected first throw in the theta 1 in the BG. Due to the flow of this charge, the deflection produced can be represented as phi n by R1 plus G is equal to K into theta 1. Now another resistance R2 is included in the resistance box, and the experiment is repeated. Again, corrected throw will be getting in the scale, so which is represented as theta 2. Then the equation for this can be written as phi n by R2 plus G, which is equal to K into theta 2. So we have got two equations for theta 1 and theta 2. Now what we are doing is, and these steps are purely mathematical. From 1 and 2 we can write phi n as this, just rearranging the terms, and from this we can write down G, and from 2 phi n can be written like this, and G will get like this. So from these two we can equate these two equations so that we will finally reach the value of Ks phi n by r2 minus r1 into 1 by theta 2 minus theta 1. So this is the charge sensitiveness which is measured through the Hibbert's magnetic standard or HMS method. Okay.